Welcome back. Today is September 28th, and we're going to pretty much almost like start chapter 6. We started off on Friday, but we only touched a little bit of it. And so my goal is to prepare you for this chapter now. All right, so we have a lot to do. We have lots of reactions, reaction names, and mechanisms. All right, so to help you get better at OCHEM, I noticed that there's only one thing when it comes to reactions that will help you understand them and sync it in your long-term memory, and that is to creating a reaction list or reagents list. All right, so if I go, let me show you something here. Let's say I go to my instructor's notes. Let's see, chapter 6. I'll take this one. From this point on in the ball game, every time you come across something like this, or if it doesn't have this table, but you see a new reaction, I want you to write that down and create a log of reagents and reactions. So I have put this on Canvas for you. For those of you planning on taking the second part, this reagents list will help you, even if you don't take my class next semester. If you take it with someone else, just continue having a reagents list. This is the language of organic chemistry. If you know the reagents, the function, and also the name of the reaction, and you write it down with an example, you should be able to memorize that type of reaction. So I'm gonna do the first example for you guys. So according to my notes, and remember we have flipped the classroom, so you have all this. You're responsible for knowing all these named reactions now. Notice that first we have hydrohalogenation. So why is it called like that? Well, you have a hydro, you're adding a hydrogen and a halogen, and here you have it. Here you have it. Hold on a second. Here's your hydrogens, and here are your halogens that you're putting in a alkene. All right, so this is the first type of reaction you have seen from chapter 6. So what I would do, if I was you, I'll start my reagents list and put HCl, HBr, and HI. They all are the same thing in terms of the way they react with alkenes. And then the function. So here you have add a proton and a halogen to a double bond. So write that down. This reaction adds a proton and a halogen. You can say X for halogen. Let me write it down for you so that as a proton and a halogen. Let's see, that's not what I would look. And an X halogen, where X could be Cl, Br, and I, to a carbon double bond carbon. So an example of it. So if you have this, so before that, I'm gonna write down the name of this reaction. This is called hydrohalogenation. And you can add more. Say, for example, you can make this bigger by adding enters here. So you can make that bigger if you want, the box. So it's up to you. This is a Word document. You can manipulate it to your style, and that is fine. I think I had it like this. So yeah, I don't need that much room. So I'm gonna write down my first example, and I know that this reaction will put a hydrogen where there's more hydrogens, where the rich gets richer, and the chlorine will go here on the most substituted carbon. All right, so that will be how I will love you guys to proceed, because if you do this, you will learn more. So be proactive. Don't let this blank reagents list be forgotten in Canvas. From this point on, keep it as a journal. Every time that you see a new reaction, write it down, write the example, even write down the name of the reaction. That's going to give you the desired vocabulary in organic chemistry. So when you see something like this, oh yeah, I'm dealing with a hydrohalogenation. When you see the next example, like this, this is hydration. You know, it's hydration of alkenes, but you just say hydration, it's fine. You know, the reagents, you put the reagents down, the function, and on my notes, I tell you something that is important. But for your best learning, instead of writing notes, the best notes you can take, it's writing down a reaction scheme. All right? Okay. So let's go back to the class now. I'm here. So last time when we met, we were predicting the products, and all of these reactions that you see here, with the exception of 5, they're all hydrohalogenation reactions. Let's see. So all of these are hydrohalogenations, because you add a hydrogen and a halogen. One thing that I forgot to mention Friday, was that the double bond is electron rich. So here where you have your electron negative going to your E+, your E+ is your proton now. So I said that electron negative or electron rich always attacks electron poor. All right. So when you do this, notice that there is a bond between H and the Br. So the double bond attacks the hydrogen, and the electrons here from the bond go to the bromine. All right, these are covalent bondings because you have two non-metals. And so for all these two, I forgot to put this little arrow here. We attack there, and we transfer those electrons from the bond into the bromine. So basically what I'm saying is, for the HBr, for example, molecule, you have 2 electrons. When this is taken, these 2 electrons are transferred to the bromine. And that's why the bromine, in this case, well, I didn't, like in this case, right here, we'll have 8 electrons around it, and then it can do a nucleophilic attack. All right. So, but mechanisms have to be learned separate from reaction schemes. So this question number 1 is asking you to predict products. So you just simply need to figure out the final product. So how? Like we did on number 3. So check this out for number 4. So I have a double bond, and then I'm going to add hydrogen iodide. So this is going to attack the hydrogen. This double bond attacks, and then the iodine is going to grab the 2 electrons. So when that happens, this this carbon right here has an H. This carbon right here has a methyl group. So according to Markovnikov, the H from the acid will go to this carbon right here. So without the mechanism, I'm going to do it stepwise. So here, this is what I will have. I'll have this first thing form, and then notice that now here I have formed a carbocation. This carbocation is it tertiary, secondary, or primary? Anybody? What do you see on this molecule here, this intermediate? This one. Is it primary, secondary, or tertiary?
Tertiary.
Yes, very good. It's tertiary because we have 1, 2, 3 carbon connections. And this carbon too, also, make sure you know that this is an sp2 carbon. It's absolutely flat. It's a trigonal planar structure. The p orbital that contains the charge, the plus charge, is empty. And it will be in conjugation if you have a double bond somewhere, but you don't in this case. So right now this molecule is pretty flat. At least that part, the part of the carbocation. So now this attacks here, and you make that. You can omit the hydrogen because now you know what this forms. So basically we're looking for this answer. All right, this is an intermediate that I don't necessarily need to write it down because I'm trying to predict the products, but since I'm teaching you, I always write that down just in case. So does Markovnikov rule matter here, yes or no? Does it matter right here when we do the, where do we put the hydrogen? That's what I'm trying to say here. Does it matter?
Yes.
Yes. Markovnikov rules matter. So we need to start rioting if you don't remember that. No, I'm just kidding. So, yes, so that's what this goes. All right. All right, so how about this last question here? Notice that you have 2 halogens, but like in any relationship, there's always one person that is more electropositive, and there's one more person that is more like electronegative. So because chlorine is closer to fluorine. Even though these two are halogens, chlorine is the most electronegative of the two. So iodine, if you ever see an example like this coming up on a homework or a milestone, you need to do this little analysis. Even a bromine, when we'll do bromine to bromine, one is a little bit more electronegative than the other one. Why is that? Because they're pulling, and at some point each one pulls a little bit. Obviously the net charge here is 0 for the two bromines, and there's no vector for where the pull goes. Like in this case for the chlorine, the vector will go from the iodine to the chlorine. But at certain point in the reaction, because these molecules are vibrating, one will be more electropositive or partially plus, and then the other one will be more electronegative or partially negative. All right, so let me erase that. All right, so without further ado, I can just say, so question I have here, I'm gonna put the answer here. Where will the iodine go? Carbon number 1 or carbon number 2? The iodine.
The carbon number 2.
It'll be carbon number 1. And why is that? If I put the iodine here, I'm making a secondary carbocation. If I was to put the opposite, notice that I have 5 carbons. If I put the iodine here, I'm making a primary carbocation, which is not stable. It is the least of the stable ones, the very least. So I'm forced to put the iodine here so that the electronegative chlorine comes and attacks here. And now you have this. So the question I have here, does Markovnikov rule matter? Yes or no? Yes, because we're looking for stability of the carbocation. The carbocation will determine which species forms more preferably. Preferably. So notice that your nucleophile always goes to the most substituted carbon. Most substituted carbon right there. Most substituted carbon right there. Why is it the most substituted carbon? 2? Because you have 1, 2 connections, whereas carbon's 1 only has 1 connection. All right.
So does the most electronegative atom always go on the first carbon?
The most electronegative atom will go to the most substituted carbon. That's what I'm trying to say. You got it?
No. Can you explain that?
Yeah. All right. So let me open another tab. A page. So notice that when I'm here and I have 2 hydrogens here and no hydrogen here on this carbon right here, there's no, because I have 2 CH3s. If I add acid like ACl to this, the double bond's gonna grab this H and we make this. I'm going to put this in there, but know that there's 2 hydrogens there too. All right, so I'm going to erase them. I put that, and then the plus goes to the most substituted carbon. This carbon has 1, 2, 3 substitution. Therefore, this is a tertiary carbocation, C+. And then the chlorine that is hanging around is going to go and attack it. And then you'll end up with this. All right. Also so notice that here the chlorine goes to the most substituted carbon. All right. You don't need to write this H. You can delete that. And if you write this down like this is fair game. Because you're telling me, hey, I put an extra hydrogen right here. So now that group is a CH3 instead of a double bond CH2. All right. Does that make sense? Let's do another example.
I
Yes.
was just wondering, like when you have the chlorine and then the iodine.
Oh. Let's do it with the chlorine and the iodine. So this is partially plus, this is your partially negative. According to the electronegativities, chlorine is closer to fluorine. This double bond goes after the partially plus. Remember, we're doing this from electronic rich to electronic poor. Electron rich, electron poor. And so when you do that, your iodine will go here and your chlorine will attack the tertiary, in this case, tertiary carbocation. So I'm gonna leave it here. And then you end up with this. Does that make sense now?
Yes, thank you.
You're welcome. So notice that chlorine goes to the most substituted carbon. All right. And iodine goes to the least substituted because he is the one that is acting like a proton for the hydrohalogenation. All right. Let's see. Let's go back here. All right. All right. So now this is interesting because when it comes to research or when it comes to reagents in OCHEM, in a reaction you have 3 components of the reaction. You have reagents. No, let's not that. You have reactants. Let's call it like that. Reactants, because they're reacting. Here on this block, on top of the arrow, will be your reagents. And then you have products. All right, so those are the 3 components of a reaction. And so I could draw the reagents and the product, you give me the reactants. I could draw the reactants and the reagents, you give me the product. Or I can draw the reactants and the product, you give me the reagents. So that's it. So it allows for several combinations, but it's all geared towards knowing to see if you're mastering the subject. All right. So we're going to predict the reagents of the following reactions. Whenever possible, allow carbocation rearrangements. Okay, so it's important you guys know carbocation rearrangements. What does it mean by that? So hopefully you are keeping up with my recordings, because it's very difficult to think that you're not catching up, because if you're not catching up, you'll be extremely behind when we come to the practice homework. Because when I do the practice homework, I'm assuming that you have seen everything from the chapter, and so when I do this kind of thing, so then I'm thinking, hey, they know, because I already taught it on the recordings. But check this out. So for those of you who I haven't caught up yet, so let's say we have this, and let's say I'm gonna do a hydrohalogenation. Let's say I add HBr to this. When this double bond grabs this H and it kicks this bromine out, you're gonna form a secondary carbocation, right? I'm gonna start now omitting this hydrogen here. The hydrogen went there. All right, now you have a CH3 group there, and you have a carbocation here. But notice that this is a secondary carbocation. If the molecule can migrate a proton and do a 1,2 hydride shift, you can improve the carbocation stability. So here, notice that I started with a hydrogen here. This hydrogen is still there. This hydrogen could do a 1,2 hydride shift. It'll do this. It'll jump over there. All right. And so when it jumps, let me write it down. This is a 1,2 H hydride shift. Why is it a hydride? Check this out. You have 2 electrons here on this bond. Both of them are going to jump. So let's recap what you know about hydrogens. This is a hydrogen atom. This is called a hydrogen atom, or a hydrogen, also known as a radical, because it has only 1 electron. All right. Now check this out. If this hydrogen atom loses 1 electron, what do you get? You make an H plus. This is called a proton. If this hydrogen atom gains 1 electron, then you make an H with 2 electrons, which now has a negative charge. This is called a hydride. Please take notes of this. The hydride is a nucleophile, and it's also a base. It's a nucleophilic base. So when these 2 electrons from the hydrogen jump to this carbon, excuse me, I was eating oatmeal again, And those little pieces of oatmeal get in my throat sometimes, but it's delicious. You're gonna be making this. So here you have a hydrogen already in there. Notice that a carbocation is flat. So on that structure you have this. That's what it looks like. So it's sp2. This is an sp2 carbon. So that's what you have over there. Once the H jumps, now you're gonna have two hydrogens here, and now your carbocation is gonna be right there. You see that? Now this went from a secondary to a tertiary carbocation. How cool is that? And so the bromine that's hanging around here is waiting for its turn to attack. So this bromine, it's electron rich. And so it can go, and it prefers the tertiary because it's more stable. and also a byproduct will be this one. This will be a byproduct of the reaction. That's why in organic chemistry you always have several products because of the different rearrangements going on. So the major product will be the attack on the tertiary carbocation, and so that is preferred. So you will have here this. So if the question asks you write the major product of this reaction, you have to say it's this. But you also make a little bit of this, the one on the left side.
Is the one on the left considered minor?
Yes, it's your minor. Yeah, absolutely right. Yeah, so that's why you're looking for. And we're gonna practice some of that. Now, some of the reactions that I have here are fixed. They don't have carbocation rearrangements, but some do. All right, let's go back to the practice homework. All right, we're going to predict the reagents of the following reactions. Whenever possible, allow C plus means carbocations rearrangements. State if the reaction proceeds via Markovnikov, anti-Markovnikov, or neither. All right. So notice that this reaction puts the OH in the secondary carbocation. That means one hydrogen goes here and the OH goes here. So I'm not gonna do the mechanism for this because I had the mechanism in the back. Actually, I should do the mechanism first. Let's do that. Let's go back to, let's revise this synthesis after we do the mechanisms. What time is it? Okay. All right, let's do the mechanisms first because some of these mechanisms are really, really cool and you need to understand what's happening. Notice that this reaction has a name. So I put a box here. Anybody knows the name of this reaction in this awesome morning? And what is the name of this reaction? You can look it up. I'll give you a minute. You can look it up on my notes. But it's time for you to start thinking in terms of named reactions. Now I'll tell you something that's going on in the world right now. because of the social justice unrest that the US and other countries are having. Some chemists are starting to complain about name reactions. Don't take this, from me. I mean, I'm just telling you the news, and so you know what's happening. Some chemists complain that most of these name reactions, especially these ones, don't have much of like last names, but there's a lot of chemistry named after white people, and so most of the chemists that started this thing of naming their own reactions were of European descendancy. And so that's now creating a big debate, especially with the American Chemical Society. There's been some blogs about that, and people want to get real name reactions. And I'm like, how are we going to be teaching OCHEM if this for years have been, the language of organic chemistry? So we're gonna be like, for example, learning about the Wittig reaction. The Wittig reaction produces an alkene and phosphorus oxide. So it will be very difficult to teach, this is the alkene formation phosphine oxide production reaction. I mean, instead of just saying the Wittig reaction. You see what I'm saying? It's going to be extremely hard if, we continue with this thing on trying to apply everything from social justice to, to what's happening in the world right now, to especially organic chemistry. It will be extremely difficult for me and for all of my peers that teach OCHEM to be naming and teaching you something that I need to be politically correct. So I don't know what's going to happen. But in the meantime, nothing has been changed yet. So I'm going to teach you what I know with the name reactions, okay? So I'm all pro-justice. Don't take me wrong. I'm all pro-justice. But because I hate discrimination. But heck, if someone that was as wise know name a reaction that's helping me, to better my life, to make a drug or something, I don't have a problem with that. I don't have a problem. I don't even see the skin color on the name reaction. I'm telling you that right off the bat. It's simply a name for me. All right. So enough said of that. So let's go over here. This reaction. What's the name of this reaction? Anybody found it? Yes. Let me see the chat. Yes, Ruben Lozano. Very good. So oxymercuration. But so that is the first part of the name. Oxymercuration. But there's also a second part called demercuration. This type of reactions are cool because they don't have like a last name. All right. So if I ever invented a reaction, I actually wouldn't put my name on it. I just call it what it does. Like in this case, this would be oxymercuration-demercuration instead of the Odin's reaction. I think that's just too much. All right, so here's the mechanism. So here you have mercury diacetate. So mercury diacetate is expressed like this. All right. In parentheses means that you have two acetate groups. So one is to the left, and the other one is to the right. All right, and so this is a dissociation reaction. It's in water, and so because it's a dissociation reaction, simply you put a double-headed arrow. Double way arrows. So these double way arrows are also always used for acid-base reactions. All right. So here the mercury. So here you will break this reaction. So let's see how that works. So mercury. So one of these bonds breaks, and now you have mercury acetate with one lone pair and a plus sign here on the mercury, and on the other side you have the acetate group. The acetate group, this is the same thing as, this is your acetate group. It has a CH3, a carbonyl, and an O minus. This is your acetate. All right. So let me put this in the parentheses so it looks nice. All right. So the cool thing about this reaction is that it forms a tri-member cyclic intermediates. Check this out. These reactions, I call it the double slap. This is my slang term for it. So yeah, they can change everything they want according to name reactions, but I'm actually going to add my terms too, if I can. Please allow me to call this, and I'm going to introduce you to the double slap. So imagine two people fighting, and here's the mercury it has a lone pair, but it also has a plus. The double bond is the electron rich because it doesn't have a charge, but it has a pi bond. It sees the plus and say, hey, come here, and then slaps the mercury, and the mercury see, oh yeah, take this, and then double slap it. So one slapped one, the other one slaps the other one back to back. All right, and now you have this. Notice that you will have a tertiary three-member intermediate, three-member ring intermediate. So I'm going to put this methyl group up, but I'm going to show you that you have both. I'm going to also notice that you're going to have an elongated bond. One will be longer than the other one. The one on the top will be longer. This one wants to break. It's not a perfect triangle. It needs some purpose. It's slanted. All right. So you have that plus, when I write this down, plus enantiomer. You can just write this down. If you are on a test or something, if it was a paper test, because obviously we won't be able to draw much. I had to do all the drawing for you. But the enantiomer of this molecule will be this guy. So now we have chirality form. Now this group could be down, the methyl group could be down, and now this mercury complex will be up. So that's what it told it is the enantiomer. Now, on a mechanism, notice that I'm interested in finding the right product. That is my job, to prove this molecule exists and to get to it. All right. So I need to pick the structure, the intermediate structure that will get me there, and it's the one on the top. So notice that now you have water here in the synthesis. If you have water, or if you have an alcohol, let's say you have CH3OH, this oxygen from the water or the alcohols will be your nucleophile. So this water now comes and attacks there. It's going to break this bond. So notice what's happening here. Bond making, bond breaking, right? And so now you have this. This is another intermediate. So if you were like doing this synthesis, this would be your reactants. Then you have a bump here. That's your first bump, a transition state. This is a transition state right here. And here's the final product of the first step, which is a reaction intermediate. Then become a reactants of the next step. And so notice that when you attack here on the water, this methyl group is pushed down. So it's going to be forced down. The OH, the H2O will come from the top. And you have one lone pair with a plus. And now this group, this bond underneath, it stays dash. All right. So now this molecule is unhappy. You do deprotonate, and so you take acidic. The acetate group comes and grabs this H, and these two electrons that are right here on this bond are transferred towards the oxygen. And I gotta hurry up here. I'm almost there. And then you form this. This is your final product here for the oxymercuration. Notice that it's an oxy because you form an OH. And this is a mercuration because you still have mercury here. All right. So this is your oxy mercuration part. The demercuration happens next, and it's simply sodium borohydride, which is, it looks like this. And these two electrons are gonna go and attack here and are transferred over there. Oh, what happened with this reaction? The first one, we made acetic acid from the OAC, or you can just write it down like this. All right, and now your final product here is this one. Notice that there was no carbocation rearrangement on this reaction. It's really good. All right, so this is the final product for this reaction. And that's all I have for you guys. I'm gonna stop the recording here now. Thank you.